So these are the 7 crystal systems that you have, what you can see on this table. Okay. Now you would also find some letters here like P, I, and F. So in order to understand the crystal structure fully, we also need to understand the meaning of these 3 or 4 letters that we have here: P, I, F, and C. P means primitive, and we have already defined this before. This is a cell where the lattice points are only at the corners. Okay. But we have seen that there could be also lattice space arrangement of points wherein you also have points apart from corners in other positions, in other lattice points, right? So those are taken care by the other 3 letters that you see: I, F, and C. Okay. I means body centered, and the word is actually a German word. Probably said as Innenzentrierte, which stands for body centered. That is why we have this I and not B. Okay. So I stands for body centered. That means you have a lattice point at the center of the body of that cell, at the body center of the unit cell. We will see all the diagrams in a while. And F stands for face centered lattice, where you have a lattice point at the centers of each of the faces of the unit cell. Okay. Then there is one more, that is C. You would also find A and B. I will tell you the meaning of that. This means base centered or C centered, wherein apart from corners you have lattice points at the center of 2 opposite faces. Okay. If these 2 faces are perpendicular to the C axis, the Z axis, then we'll call it C centered. If it is perpendicular to the X axis, we'll call it A centered. Similarly, if it is perpendicular to the B axis, we will call it B centered. Okay, A centered, B centered, or C centered, depending on which 2 faces you have chosen to put that lattice point at the center of both the faces. Okay. So for example, if it is C centered, we will have a cell like this. So we have lattice points at the corners, and apart from that, if it is C centered, we will have 2 more lattice points at the centers of these 2 faces, one here and another there. Okay, so this is known as C centered, but you can also have A centered and B centered depending on which two faces you have chosen. Okay. Now, what is the point of discussing all this? Why not stop at that number, that 7 crystal system, and say that all the structures will lie within these 7 systems? But as I said, when you talk about these 7 systems, we are only talking about the primitive cells, where you have the lattice points only at the corners, but there are other possibilities where you have a lattice point apart from the corners also. So that is why we need to talk about how those points can be accommodated in a space lattice going by the periodicity of the crystal. Okay. So it has been found that there could be 14 such arrangements. Somebody found this. He did all the studies, systematic studies on crystallography, and found that there could be 14 such possibilities, 14 lattices. The name of that person, Bravais. Okay. So we call all these lattices as Bravais lattice because he was the one who found out that there could be 14 such possibilities within which all the crystal structures can be accommodated. But even before him, 13 years before him, there was somebody who actually came up with this idea of this kind of space lattice. But unfortunately, he overcounted just one. Instead of 14, he said there are 15 such lattices. Who is this person? Anybody? 13 years before he already did it, but we don't even know his name today. Just for one mistake. Instead of 14, he counted 15. He overcounted just one. Okay. M.L. Frankenheim, a German physicist and crystallographer who did all the systematic studies on crystallography and came up with 15 lattices. For all the 14, he was right, except one. Okay. So today, for that one mistake, we do not know this person. He came up with this in 1835. Okay. And 13 years later, the French physicist and crystallographer Auguste Bravais corrected that and said that there are 14 lattices. And today these are known by his name, 14 Bravais lattices. Okay. We would also try and understand as to what led Frankenheim to believe that there are 15 and not 14. That understanding is also required here for us to completely understand the crystal structure. You remember what I said about unit cells, because so far we are only looking at the unit cells and trying to define a crystal structure based upon that. Whether this idea at all is correct or not, that is first thing that we need to understand. If you want to classify or define a crystal structure, is the unit cell enough for that, or are we missing something? So if you consider just a simple structure here, for example, let's say I have an arrangement of points like this. Is this a lattice? Yes, it is. We have a periodic arrangement of points in space where every point has identical environment. So I can sketch out a unit cell like this. And in the 2D space, this will be a rectangular centered unit cell, because at the center also you have a lattice point, right? So this is a rectangular centered lattice. If I want, I can also sketch a unit cell like this in the same lattice. Can I not? It's up to me. It's up to my convenience how I connect these dots, how I connect the lattice point. You remember, this is what we discussed while talking about unit cells, that it's a convenient way of connecting the lattice points, and there could be infinitely many number of ways that one can connect the lattice points, right? So instead of a cell like that, instead of a unit cell like this rectangular centered, I can also draw a cell like this, which is basically a diamond or rhombic primitive, right? Because here we have the lattice points only at the corners. So you can see a rectangular centered lattice can also be described by a diamond or rhombic primitive unit cell, depending on how I have chosen to connect the points. So there is a confusion that in the same structure you can come up with two unit cells, and now if you take the unit cell as the basis for a crystal structure, then there is a possibility that one can overcount, right? So this might have led Frankenheim to overcount just one. May not be the exact same lattice, but while he was doing his work on the space lattice, this kind of possibilities were there, and probably that led him to believe that there are 15 lattices. 13 years later, Bravais found that mistake and corrected it to be 14 lattice, and today we know all this by his name, 14 Bravais lattices. So it have 7 crystal systems, and in each of them we have the Bravais lattices. Put together we have 14 Bravais lattices. The distribution is given here. For the cubic, we have primitive, which is also sometimes referred to as simple. So simple cubic and primitive cubic are synonymous. Okay. Then we also have body centered cubic, BCC as we call it, and face centered cubic or FCC. So in the cubic system we have 3 Bravais lattices. In the tetragonal system we have 2, primitive and body centered. In orthorhombic we have all 4, primitive, body centered, face centered, and also base centered. Okay. Then comes hexagonal. Here we have only 1, primitive. Then we have trigonal or rhombohedral. In that also we have primitive. In the monoclinic system we have 2, primitive and base centered, and in triclinic again we have only primitive. Now if you count, it comes to 14, the 14 Bravais lattices. Okay. I'll quickly show you the pictures of these. Starting with cubic, in the simple or primitive one, we have lattice points only at the corners, right? So that is what we call as primitive or simple. Then we have body centered cubic or BCC, in which apart from the corners, you have a lattice point at the body center of this cell. Okay, this point over here. All right. Similarly, in the face centered structure, apart from the corners, you have a lattice point at the centers of each of the faces. So that is face-centered cubic or FCC. For tetragonal, we have two Bravais lattices, simple tetragonal and body-centered tetragonal or BCT. So here we have 5 and 9 more to come. So in the orthorhombic, we have 4, all the 4, simple body-centered, face-centered and also base-centered, in which you have a lattice point at the center of a pair of opposite faces. Okay, and if that face is perpendicular to the C axis, then we call that as C-centered, which is the case here, what you see on the screen. If it is perpendicular to the A axis, we can also call that as X-axis. Then it will be A-centered. Similarly, if it is perpendicular to the B axis, we can call that B-centered. Okay. In monoclinic, we have two, simple monoclinic and base-centered monoclinic. And in these three, we have one each: rhombohedral primitive or simple, primitive hexagonal, and primitive triclinic. Okay. So 7 crystal systems and 14 Bravais lattices. All right.